Good morning. So, welcome back to the class. Okay. I think in the last class, I was discussing the check for sliding. Okay, in the cantilever retaining wall. So, there is 3 checks for the stability of the retaining wall. One is the check for soil earth pressure, that we have done it. The second one is the check for overturning moment, that also we have completed in the last class. Okay. The third one is check for sliding, that also we did it in the last class, but it came unsafe. Okay. So, to overcome that, so we have provided the shear key. Let me continue with that. So, we have provided the shear key. So, we have provided with the shear key. So, this portion is called as the shear key portion. Okay. So, now, so whenever you apply the pressure in this direction without shear key, so it means that the retaining wall is moving in this direction. So, to avoid that sliding, so we need to provide this shear key. So, it is a resisting element. So, I think in the last class I have explained this portion we will be having the passive earth pressure, and all in this portion you people will be having the active earth pressure. Okay. So, now as it in the last class it was not safe. So, now we have provided the shear key. So, what is the width that you people are providing? Same as the stem width, bottom stem width. Then what is the depth you people will be providing? So, for timing I will be calling it as A. So, now Ka in the last class only we have calculated sin 30 by 1 minus sin 30. So, it is 3, and assume A is equal to 200 mm. Here also the same thing, factor of safety against sliding, factor of safety against sliding. I need to check same formula, that is mu into sigma w divided by ph, okay, plus, okay, this is the resisting force. Which is the resisting force? An addition that we have given, it is nothing but the shear key. So, resisting force from shear key, I need to add that particular force, resisting force. Okay. So, now what I need to do here is, I know the value of mu, sigma w, ph and all, I need to calculate the resisting force. Resisting force. Okay. So, resisting force, it is due to the addition of the shear key. Due to the addition of shear key, passive earth pressure comes into picture, the coefficient of passive earth pressure Kp into this resisting force I need to take. So, I think I have already explained you people. So, stress is equal to load by area. Load is equal to stress into area. Okay. So, stress is upward soil pressure into area. So, now what is this upward soil pressure? Okay. So, for that thing I think we have done the check for soil earth pressure. So, while doing the check for soil earth pressure, I will be writing a diagram over here. Okay, observe. So, whenever you try to apply the load, okay, so this tries to overturn. So, usually the soil pressure distribution will be like this. So, here the pressure will be more, and what is that value? It is 102.2 kilonewton per meter square. Sir, where you got this value? So, this value is nothing but the sigma max and sigma minimum value that we have already calculated. So, what is the value of sigma minimum? So, sigma minimum value is it's 42.09. It's 42.09 kilonewton per meter square. Now I have added a shear key over here. Yes or no? So it means that I want to know what is the soil pressure at that particular junction. I think you people know what is this distance? 1.2. Yes or no? Then what is this particular distance? It's 2.05. What is this distance? It's 0.35. So now what I want is, let me consider this as 0, and what is this total width? It's 3.6 meter, B dash. So if this is 0 and this is 3.6, I want the soil pressure at 1.2 meter. I want the soil pressure at 1.2 meter. I think using the calculator by doing interpolation, I think you people know how to calculate it. So only for 1 I will be showing it. For 0, it is 102.2 kilonewton per meter square. And for 3.6, it is 42.09 kilonewton per meter square. Okay, then I want it for 1.2 meter. So what is this particular value? Using interpolation, using the calculator, you can easily do the interpolation. So I will be directly writing the value. For 1.2, it is 82.18. It's 82.18 kilonewton per meter square. Similarly, if this is 1.2, add 0.35 to it. So from the starting till here, it is 1.55 meter. So similar concept. For 0, it's 102.2 kilonewton per meter square. And for 3.6, it's 42.09 kilonewton per meter square. I want for 1.55. So for 1.55, how much? Use the calculator. So I have already the value. So directly I will be writing it. It is 76.38. 76.38 kilonewton per meter square. 76.38 kilonewton per meter square. So now I am concentrating on the upward soil pressure where I will be placing the shear key. So this is the portion where I will be placing the shear key. Out of these two values, which is highest? It is 82.18. So let me consider that value. I know the value of Kp. It is 3. Upward soil pressure is 82.18 kilonewton per meter square. Then I need to calculate the value. I mean the area. So area, observe here. So upward soil pressure, because the soil will be resisting. This shear key will be resisting the soil in this particular portion, not from the bottom, from this particular portion. So that's why what you need to do is, you need to take only this portion. Area I want, breadth into length or length into breadth, whatever it might be. So this A into till what distance it's go? Because if I want to resist the soil, okay, so the portion that are coming in contact is this portion until what distance? So that's why A is 200 into 1 meter. So 200 mm, instead of in meter, I will be writing it in 200 mm, it is 0.2 meter into. Area is nothing but, that is the depth into length. Length is 1 meter. So what is the value that we got? So it is 49.31. 31 kilonewton. So let me substitute it. Therefore, factor of safety is equal to mu is 0.55 into sigma W. So it's 259.79. It's 259.79 plus this resisting force whole divided by pH 95.04. I think that value is correct, I guess. Yes, 95.04. So finally we got it as 2.02. In the formula, what I have told, it should not be less than 1.55. Now it is greater than 1.55. Hence it is safe. See? If after considering the shear key also, here if we got it as less than 1.55, so then what we need to do? We need to redesign the shear key. Sir, how to redesign it? Just increase the A value. Instead of 200, let me go with 300. Okay, so this is how we need to do it. So this completes the stability check of the retaining wall. That is the check for soil earth pressure, the check for overturning moment. The third one is the check for sliding. So till here, whatever we have done, it is the analysis part. Now we are entering into the design part. So there are three design that needs to be done in this design of cantilever retaining wall. The first one is the design of stem, the vertical structure in the retaining wall. The second one is the design of base slab. In that it will be divided into two. One is the toe slab, design of toe slab, and one more is the design of heel slab. So first let me take up the design of stem. Now let me take up the design of stem. I think the first step it was the dimensions. So I think the first step it was the data. The second step it was the dimension of the retaining wall. The third step it is the check for the stability of the retaining wall. And the fourth step it is the design part, design of stem. Design of stem. Now in the starting of the class, okay, not today starting, so in the starting of the cantilever class I have told you people the general procedure. If I want to design, okay, so what is the final thing that we are left out with? Either the number of bars or the spacing of bars. Stem, it's a vertical thing, and in the horizontal direction it is a huge one, so we'll design it as a slab. Okay, so whenever slab come into picture, it is the spacing of bars. If I want to know the spacing of bars, I want to calculate the area of steel. How much steel? It depends on the bending moment. How much bending moment? So it depends on the loading. How much load, dimension, all those things we have calculated. So now let me directly take up the values. So let me directly take up the value of the bending moment. So mu. Okay, so just a moment. So it's mu. So mu of stem. So where you people will be getting this value? Okay, while doing the dimensions of the retaining wall, that to the bottom stem thickness. Bottom stem thickness. We have calculated a moment. Whether you people remember that, I have taken a section. So x6 or 1 I have taken a section. I think x6. So that particular value we need to take. That is mu of stem. That is from bottom stem thickness. From bottom stem thickness, we have calculated the value of mu stem. What is that particular value? It's 219.62. It's 219.62 kilonewton meter. It's 219.62 kilonewton meter. So I think you people remember. So while calculating the thickness, I have taken a section like this. Yes or no? X6 I have called it. And I have drawn the pressure diagram only for this. Here I have written it as P into small h. This is Ka into gamma into small h. All those things. So if I want the moment about this junction, so it's pH into h by 3. So this I have already calculated in the last previous classes. So from there I have taken it. Now you people know the moment. You people know the moment. Whenever you know the moment, you can easily calculate the area of steel. Let me calculate the area of steel. How to calculate the area of steel? Which formula you people will be using? I think you people know, while doing the RCC, you people were using mu is equal to 0.87 FYAST into D into 1 minus FYAST divided by FCK BD square. So the same formula I will be using it now. So observe. And before going with that, what is the depth of that stem? Overall depth in the horizontal dimension, it is 0.35, or else I can say 350 mm. So what is the effective cover I have assumed? Remember, what is the effective cover that I have assumed? 60 mm. Okay, then what will be small d? Small d is nothing but effective depth is nothing but the overall depth minus the effective cover. So it's 290 mm. So now I will be calculating the area of steel. So how to calculate the area of steel? So we know that mu is equal to 0.87 Fy AST into D into 1 minus Fy AST divided by FCK B into D. Let me check it whether the formula is correct or not. Yes, 0.87 Fy AST into D into 1 minus Fy AST divided by FCK B into D. I know the value of mu. So it's 219.62. What is the unit? Kilonewton meter. But Fy is in Newton per mm square. FCK is also in Newton per mm square. Breadth and depth, that also we will be substituting it in mm. So what I will be doing is, I will be converting this kilonewton and meter to Newton mm. So just multiply it by 10 to the power of 6 is equal to 0.87. What is the grade of steel? I think it's 415. Just cross check it. So yes, it is 415. AST only we are calculating. Into D, it's 290. Into 1 minus Fy is 415. Into AST we are calculating it. Divided by FCK is 20. Breadth I will be leaving it for time being. Depth 290. So in the previous classes only I have told you people, this stem I am designing it as a slab. Okay, slab, it is usually a bigger structure. Okay, so I will not be calculating the number of bar, instead I always go with the spacing of bars. So here I don't know till what distance it is, so per meter I will be taking. So breadth I will be taking it as 1000. So use the calculator and solve option in the calculator. Directly you get the value of AST. Directly you get the value of AST. I have it, I will be writing it directly. It is 2570 mm square. Okay. Observe here, actually we need to check for AST minimum. But as the procedure is lengthy, let us avoid small steps, I can say. So what? Just by seeing the value of AST, it is 2570 mm square, 2570 mm square. So if I want to check the AST minimum, it is 0.12% of gross area. It will come less. So let me not check it over here. If it was somewhere around 300 or 400 mm square, then I would have gone with the AST minimum. For time being, I will not be doing that. As it is a slab, so I need to go with the spacing of bars. Yes or no? So how to calculate the spacing of bars? We need to assume some dia of bars. Usually for retaining wall. Okay, so we usually go with 12, 16, maximum 20, not more than that. 20 it's a rare case. Okay, too much of huge load it is coming, then we'll go with that. If not, we stick on to 16 or 12. For time being now, I will be sticking on with 16 mm dia bars. Sir, how you come to know? Nothing like that. It's just by practice, that's it. As you people don't have the practical idea, so just go with 12 or 16 mm. Okay. So how to calculate the spacing of bars? So spacing of bars is given by pi by 4 into d square divided by the total area into 1000. So the final value is, it is 78.25 mm. So approximately it is 3 plus inch. It is approximately 3 plus inch. Okay, for 3 inch it is 75. So it is little bit more than that. So it is 3 plus inch. So now whatever the spacing that we got, I need to check with the spacing of, the standard values in the code. So what is that? For the main AST. So spacing is least of the following. Spacing is least of the following. Spacing is least of the following. The first one is 3 times the effective depth. So it is 3 into, what is the effective depth? It is 290. So 3 9s are 27, 2 6, 870 mm or 300 mm. So out of this 1, 2 and 3, which is least, so it is 78.25. So always go a little bit lower value in an increment of 5. So now let the spacing, or else we'll say provide 16 mm dia bars at 75 mm center to center. 75 mm center to center. So this is about the main bars. This is about the main bars of the stem. I need to still go with the distribution bars. I need to still go with the distribution bars. Observe here, I will be writing the 3D diagram of this retaining wall so that you people will understand. So I am just concentrating only on the stem portion. Okay, I am just concentrating on this stem portion. Here the soil is exerting the load onto the stem. Okay, it tries to bend. Don't you think that it acts as a cantilever beam? Because it is connected only at this particular junction. So it is free at the other end. So now whenever the soil is applied on it, soil pressure, so it tries to bend in this direction. So I need to provide the main bars over here. I need to provide the main bars over here. I need to extend these bars. There will be shear key also. Till there I need to extend it. Okay. Similarly, so this needs to be taken. So like this it goes. Throughout it should go like this. So this reinforcement it should continue till this shear key. Okay. So now this is the main bar. So I need the distribution bar also. I need the distribution bar also. So let me calculate. So the distribution bar.